Hi students, welcome to my virtual classroom, the new style of learning which you may be familiar with. Here you learn chemistry for higher secondary classes. The classroom offers you a set of video classes on each chapter. We start with the basic concepts of chemistry. The first unit of class 11 chemistry. Since animations speak louder than words, I have included a lot of animations in these video classes. But a warning, animations never represent the real situation. It only helps you to understand the concepts more clearly. By the way, I am Dr. Sirek Matthew, a retired professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to NEET, JEE Main and Advanced, KEEM, CUET, and other competitive examinations. This is part 1 of the chapter Basic Concepts of Chemistry. The remaining parts will be uploaded soon. If you like the video, please subscribe my channel and forward to others. Let us start with a formal question. What is chemistry? These are the iconic pictures that come to our mind when we are asked about chemistry. Classways filled with chemicals and students doing experiments in the laboratory. Okay, coming to a formal answer. Chemistry is the science that describes matter, its properties, the changes it undergoes, and the energy changes that accompany those processes. Then comes the second question. What is matter? Matter is anything that has mass and occupies space, which means just about anything you consider. These pencils, the calculator, the timepiece, your body, the air you breathe, all are examples of matter. Matter is simply the stuff, that is, the bits and pieces that makes up our universe. Yes, chemistry is the science that describes matter. Then what is science? Science can be considered as a continuing human effort to systematize knowledge for describing and understanding nature. Chemistry touches almost every aspect of our lives, our culture, and our environment. Its scope involves the air we breathe, the food we eat, the fluids we drink, our clothing, dwelling, transportation and fuel supplies, and our fellow creatures. Chemistry plays a central role in science and are often intertwined with other branches of science like physics, biology, medicine, geology, and many others. Our body consists of a lot of compounds that undergo innumerable number of chemical reactions to keep us alive. No one can be expert in all aspects of such a broad science as chemistry. Sometimes we arbitrarily divide the study of chemistry into various branches. Carbon is very versatile in its bonding and behavior. It is a key element in many substances that are essential to life. All living matter contains carbon combines with hydrogen. The chemistry of compounds of carbon and hydrogen is called organic chemistry. This is an organic compound. Here it contains two carbon atoms, and this carbon atom is attached to three other hydrogen atoms. Of course, this carbon atom can also be attached to three hydrogen atoms, and two of the hydrogen atoms are replaced by an oxygen atom, and one hydrogen atom replaced by a hydroxyl group. And this compound is acetic acid. Study of substances that do not contain carbon combined with hydrogen is called inorganic chemistry. Physical chemistry applies the mathematical theories and methods of physics to the properties of matter and to the study of chemical processes and the accompanying energy changes. These are the three main branches, but in addition, there are several other branches like biochemistry, which include the study of the chemistry of processes in living organisms. Another one, polymer chemistry, which is the study of about large molecules, theoretical chemistry, and so on. And you will study about these branches in higher classes. Such divisions are arbitrary, and most chemical studies involve more than one of these traditional areas of chemistry. Let us talk about the development of chemistry. Chemistry is, in fact, not a very old discipline. Alchemy may be considered as the medieval forerunner of chemistry, but it is no longer considered as scientific. These are prototypes of our modern laboratory equipments. Alchemy was a tradition that was historically practiced in China, India, the Arab world, and in the Europe. Alchemists attempted to convert base metals like lead and copper to gold. They also tried to prepare an elixir of immortality. It is a preparation for rejuvenation and immortality. None of these attempts were successful. They used very crude vessels for experimenting. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. Modern chemistry was developed during 18th century. Because of his accomplishments in chemistry during that period, Antoine Lavoisier, a French chemist, is regarded as the father of modern chemistry. He is most noted for his discovery of the role oxygen plays in combustion. Let us think about the nature of matter. We know chemistry is the science that deals with the composition and properties of matter. So we must study the nature of matter before diving into chemistry. Matter is anything which has mass and occupies space. Everything around us are composed of matter. The gas of the atmosphere, even though they are invisible, are matter. They occupy space and have mass. As you are aware, matter can exist in three physical states: solid, liquid, and gas. At the macroscopic, that means taking as a whole, at the macroscopic level, matter can be classified as a mixture or pure substance. When all constituent of a particles of a substance are same in chemical nature, it is said to be a pure substance. Mixtures are combinations of two or more pure substances in which each substance retains its own composition and properties. Almost every sample of matter that we ordinarily encounter is a mixture. Pure substances forming mixture are called its components. The most easily recognized type of mixture is one in which different portions of the sample have recognizably different properties. Such a mixture which is not uniform throughout is called heterogeneous. For example, a mixture of salt and charcoal. Charcoal is black and the salt probably white. So we can distinguish the components by their color. Another example is foggy air, which include suspended mist of water droplets. Similarly, a vegetable soup. All are heterogeneous mixtures. Another kind of mixture has uniform properties throughout. Such a mixture is described as a solution, homogeneous mixture, and is also called a solution. For example, sugar solution. The two components are sugar and water. Another example is some alloys, which are homogeneous mixtures of metal in the solid state. Air is a mixture of gases. It is mainly a mixture of nitrogen, oxygen, argon, carbon dioxide, and water vapor. This is a copper piece that is a pure substance. This is a heterogeneous mixture. This one is a homogeneous mixture, that is a solution. And a pure substance also is homogeneous. An important characteristic of all mixtures is that they can have variable compositions. On the other hand, pure substance has a fixed composition. Next, we consider the classification of matter. This diagram shows the general classification. Matter may be classified into mixtures and pure substances. Mixtures have variable composition. The components retain their characteristic properties. Physical methods may be used to separate the components. On the other hand, pure substances have fixed composition. The components cannot be separated into similar substances by physical methods. Pure substances are homogeneous. Properties change through chemical process. Mixtures can be classified into heterogeneous mixtures and homogeneous mixtures. In heterogeneous mixtures, components are distinguishable. They do not have the same composition throughout. In homogeneous mixtures, components are indistinguishable, have same composition throughout. Pure substances can be classified into compounds and elements. Compounds can be decomposed into similar substances by chemical change, always in a definite ratio. Elements cannot be decomposed into similar substances by chemical change. Mixtures and pure substances can be interconverted by physical change, but compounds and elements are converted by chemical change. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties and chemical properties. Physical properties are those properties which can be measured or observed without changing the identity or composition of the compound. Some examples are color, odor, melting point, boiling point, density, etc. The measurement or observation of chemical properties require chemical change to occur. Examples of chemical properties are characteristic reactions of different substances like combustibility, reactivity with acids and bases, etc. Measurements in scientific world are usually expressed in units of the metric system or its modernized successor, the International System of Units, abbreviated as SI. We use this system of units to measure the properties of matter. The abbreviation SI comes from the French lay system international, means international system. These are the 7 fundamental units of measurement, SI units. Physical property, name of unit, symbol. Length, name of unit meter, symbol lowercase m. Mass, name of unit kilogram, symbol lowercase letters kg. Time, second, lowercase letter s. Electric current, ampere, uppercase letter A. Temperature, Kelvin, uppercase letter K. Luminous intensity, candela, lowercase letters C, D. Amount of substance, mole, MOLE. Symbol, MOL. 1 mole contains exactly 6.022 into 10 raised to 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na. When expressed in the unit per mole, it is called the Avogadro number. The amount of substance The symbol is N of a system is the measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, and any other particle or specified group of particles. The metric and SI system are decimal systems in which prefixes are used to indicate fractions and multiples of 10. The same prefixes are used with all units of measurement. The metric and SI systems are decimal systems in which prefixes are used to indicate fractions and multiples of 10. The same prefixes are used with all units of measurement. The table shows some most common prefixes used in SI system. Prefix GIJA, abbreviation capital G or uppercase G, multiple 10 raised to 9, and 1 gigahertz is equal to 1 into 10 raised to 9 hertz. Mega, uppercase M, multiplies 10 raised to 6. 1 megameter is 1 into 10 raised to 6 meter. Kilo, lowercase k, multiplies 10 raised to 3. 1 kilometer is 1 into 10 raised to 3 meter. Then deci, lowercase letter d, 10 raised to minus 1. And 1 decimeter is 1 into 10 raised to minus 1 meter. Then centi, lowercase letter c, 10 raised to minus 2. 1 centimeter is equal to 1 into 10 raised to minus 2 meter. Then comes milli, lowercase letter m, 10 raised to minus 3. 1 milligram is equal to 1 into 10 raised to minus 3 gram. Micro, abbreviation mu, multiplies 10 raised to minus 6. 1 microgram, mu g, 1 into 10 raised to minus 6 gram. Nano, abbreviation is lowercase letter n, 10 raised to minus 9. 1 nanogram is 1 into 10 raised to minus 9 gram. Pico, lowercase letter p, the multiple is 10 raised to minus 12. 1 picogram is 1 into 10 raised to minus 12 gram. Then comes femto, abbreviation is lowercase f, 10 raised to minus 15. 1 femtogram is 1 into 10 raised to minus 15 gram. Mass and weight are two terms we very often use interchangeably, but these are not the same. Let us try to understand the difference between mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. An object weighs slightly less high upon a mountain than at the bottom of a deep valley. Imagine a mighty gorilla like King Kong is walking through the seashore. Let his weight be 400 kg. His mass also will be 400 kg since he is at the sea level. Now imagine that he is flying at an altitude of 10,000 meters on top of an aeroplane. Then his weight will be slightly less, say approximately 399 kilograms. But his mass will remain the same, that is at 400 kilograms. Similarly, the weight of an astronaut on the surface of a moon will be about 1/6 the mass of the surface of the Earth. This is because the gravitational force on moon is about 1/6 of that on Earth. Smaller mass and a smaller radius of moon contribute to this. Let this astronaut weigh 84 kilogram, including his spacesuit. His mass will be 84 kilogram since he is on the surface of the Earth. Imagine he is on the surface of Moon. His weight will be 14 kilogram. That is 1/6 of 84. But his mass remained the same, 84 kilogram. Because the mass of a body does not vary with its position, the mass of a body is a more fundamental property than its weight. The mass of a substance can be determined accurately in the laboratory using an analytical balance. Since we usually discuss chemical reactions at a constant gravity, weight relationships are just as valid as mass relationships. Nevertheless, we should keep in mind that the two are not identical. Volume is the amount of space occupied by a substance. It has the unit of length to the power 3. So the SI system unit for volume is meter cube. In the laboratory, very often we use smaller volumes. So for convenience, we use metric system of unit, that is the liter and the milliliters. But liter is not an SI unit. Instead, this cube and its side is 1 meter. Therefore, the volume of this cube is 1 meter cube. Now imagine a small cube within this large cube and let the side be 1 decimeter. So the volume of this small cube is 1 decimeter cube. And 1 decimeter cube is 1 liter. See, this 1 liter is a very small volume compared to 1 meter cube. And let us expand this small cube. So this is, the side is 1 decimeter and volume is 1 decimeter cube, that is 1 liter. Again, imagine a small cube within this cube and let the side be 1 centimeter. Therefore, the volume of this cube will be 1 centimeter cube and 1 centimeter cube is 1 milliliter or ml, 1 ml. Again, expand this small cube. So this is 1 centimeter. So the volume is 1 centimeter cube, that is 1 ml. 1 ml is much less compared to 1 liter. So 1 meter cube is equal to 10 raised to 3 liter. And that is equal to 10 raised to 3 decimeter cube. Because 1 liter is equal to 1 decimeter cube. And this will be equal to 10 raised to 6 centimeter cube. And a centimeter cube is equal to ml. So therefore, that is equal to 10 raised to 6 ml. So therefore, 1 meter cube is 10 raised to 6 milliliter, or 1 meter cube is 10 raised to 3 liter. Then 1 ml is equal to 1 centimeter cube, and that will be 10 raised to minus 3 liter. And again, it is same as 10 raised to minus 6 meter cube. In the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. And this is volumetric flask. Its volume is 100 ml. So up to this mark, it will be 100 ml. And this is a measuring jar. And the maximum volume that we can measure is 10 ml. Measuring jars with different volumes are available. Here the minimum volume that we can measure is 0.1 ml. And this is a burette. And the burette can transfer. This burette can transfer 50 ml. And the minimum volume it can transfer is 0.1 ml. And this one is a graduated pipette. It's a 10 ml pipette. And we can transfer a maximum of 10 ml. And also we can transfer 0.1 m. And this one is a fixed volume pipette that is 20 ml. And we can transfer only this much amount using this pipette up to this mark. The volume is 20 ml. Let us consider density. Mass and volume are related through density. Density of a substance is its amount of mass per unit volume. Now density is equal to mass upon volume. SI unit of mass is kilogram, SI unit of volume is meter cube. So it is kilogram per meter cube. Therefore, the SI unit of density is kilogram per meter cube. This unit is quite large and commonly we express density as gram per centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. This is a metal piece. Its density is very high because the particles are very closely packed. And this is a compressed cotton block, but its density will be much less than that of this one because it is not very closely packed. The specific gravity of a substance is the ratio of its density to the density of water. Both are measured at the same temperature. Specific gravity is equal to density of substance by density of water. The density of water is 1 gram per ml at 3.98 degrees Celsius. The temperature at which the density of water is greatest. Variations in the density of water with changes in temperature, however, are small enough that we can use 1 gram per ml up to 25 degrees Celsius without introducing significant errors into our calculations. Temperature measures the intensity of heat, the hotness or coldness of a body. A piece of metal at, for example, 60 degrees Celsius feels hot to touch, whereas an ice cube at 0 degrees Celsius feels cold. Heat is a form of energy that always flows spontaneously from a hotter body to a colder body, and never in the reverse direction. Temperatures can be measured with a mercury in glass thermometers. There are three common scales to measure. One is degree Celsius, degree Fahrenheit, and a Kelvin. Kelvin is the SI unit. Generally, the thermometer with the Celsius scale is calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point of water and the boiling point of water respectively. In the Fahrenheit scale, it is represented between 32 degree and 212 degree. And 32 is taken as the freezing point of water, and 212 degree is taken as the boiling point of water. In Kelvin scale, the freezing point of water is 273 Kelvin, and the boiling point will be 373 Kelvin. The room temperature is 25 degree in the Celsius scale, while on the Fahrenheit scale it is 77 degree. In Kelvin scale it is 298 Kelvin. The Celsius scale and the Fahrenheit scale temperatures are interconverted using this formula. So degree Fahrenheit is equal to 9 by 5 into value in the degree Celsius plus 32. Kelvin is equal to value in the degree Celsius plus 273.15. We shall usually round 273 to 152 to 273 for convenience. It is interesting to note that the temperature below 0 degrees Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. In chemistry, we measure and calculate many things. So we must be sure we understand how to use numbers. In chemistry, we study about atoms and molecules. These have extremely low masses and are present in extremely large numbers. Consider this gold coin, and it weighs exactly 197 grams. The number of gold atoms present in this gold coin will be this number, a very large number. We cannot read it. That is 602 and 21 zeros towards right. Since we know the total mass of this much number of gold atoms, we can calculate the mass of one gold atom. And this comes out to be a very small number. That is decimal place and 21 zeros 327 gram. Thus, as chemists, we have to deal with such large and small numbers. It is very inconvenient to use such numbers in our daily work. To overcome this difficulty, we use scientific notation for such numbers. Scientific notation is an exponential notation in which any number can be represented in the form n into 10 to the power n, where uppercase n is the digit term and it varies between 1.00 etc. and 9.99 etc. Lowercase n, that is the exponent, and exponent may be either positive or negative. Now take an example, that is 4,300,000 or 43 lakhs. Consider a decimal here. Now we move this decimal 6 places towards left. Then the digit term will be 4.3. So that is 4.3 into 10 raised to 6. Similarly, consider a very small number, that is 0.000348. Now we move the decimal 4 places towards the right, so that the digit term is 3.48. So the number will be 3.48 into 10 raised to minus 4. Here the exponent is negative and here the exponent is positive. And now we can write down this large, extremely large number in scientific notation. So imagine the decimal is placed here. We move this decimal 23 places towards left, so that the digit term is 6.02. So the number will be 6.02 into 10 raised to 23. Now come to this number. We move the decimal to 22 places towards right, so that the digit term is 3.27. So it is 3.27 into 10 raised to minus 22 gram. The reverse process converts numbers from exponential to decimal form. While performing mathematical operations on numbers expressed in scientific notation, the following points are to be kept in mind. First, let us consider multiplication and division. For example, consider this multiplication. Here we multiply 5.4 into 10 raised to 6 into 3.8 into 10 raised to 8. Now in multiplication, we simply take the exponents outside and we add the exponents. That is 5.4 into 3.8. That is, we add these two. That is 6 plus 8. So it is 5.4 into 3.8 into 10 to the power 14. Now the multiplication value of this is 20.2 into 10 raised to 4. So therefore, in order to write in the scientific notation, we move the decimal place one decimal to one place towards left. So it is the exponent will be 2.052, and when the decimal is moving towards left, we increase the exponent by 1. So it is 2.052 into 10 raised to 15. Consider this multiplication 9.6 into 10 raised to minus 3 into 4.8 into 10 raised to minus 5. That is 9.6 into 4.8. And now the exponent we add, that is minus 3 plus minus 5. So this is 9.6 into 4.8 into 10 raised to 10 to the power minus 8. So the product is 46.08. And now we move the decimal one place towards left. So it is 4.608. When the decimal is moving towards left, we add 1. So minus 8 plus 1, it is minus 7. So the answer is 4.608 into 10 raised to minus 7. Now consider division. 3.8 into 10 raised to minus 4, 5.6 into 10 raised to 5. So this is 3.8 divided by 5.6. And when you take the exponent to the numerator, it becomes minus 5. So plus 5 become minus 5. That is 10 to the power minus 4 minus 5. And that is 10 to the power minus 9. So the division of this one give 0.6786. Now we have to move the decimal one place towards right. Digit term will be 6.786 and the exponent decreases by 1. So minus 9 minus 1, that is minus 10. Now consider addition and subtraction. For these two operations, first the numbers are written in such a way that they have the same exponent. After that, the coefficients, that is the digit terms, are added or subtracted as the case may be. Example, here we have 3.65 into 10 raised to 4 plus 6.26 into 10 raised to 5. So the exponents are different, 4 and 5. Either we can make it 4 or we can make this 5. So to make this 5, we move the decimal one place towards left so that it becomes 0.365. Then the exponent increase by 1. Therefore, the number will be 0.365 into 10 raised to 5. Now here also it is 10 raised to 5. Now the 10 raised to 5 is common. So we take the 10 raised to 5 outside. Now we add these two numbers. So the answer will be 6.625 into 10 raised to 5. Another example. Here the number is 2.48 into 10 raised to minus 2 minus 1.34 into 10 raised to minus 4. We can either make this exponent minus 4 or this minus 2. Suppose that we convert this to minus 2. So 2.48 into 10 raised to minus 2. So to convert this number into 10 raised to minus 4, we move the decimal two places towards left so that it is 0.0134 into 10 raised to minus 2. Now 10 raised to minus 2 is common. We take the 10 raised to minus 2 outside. So it is 2.48 minus 0.0134 and the answer is 2.466. So it is in the scientific notation. So it is 2.466 into 10 raised to minus 2. Precision and accuracy. Scientists typically make repeated measurements of a quantity to ensure the quality of their findings and to know both the precision and the accuracy of their results. Measurements are said to be precise if they yield very similar results when repeated in the same manner. A measurement is considered to be accurate if it yields a result that is very close to the true or accepted value. Precise values agree with each other. Accurate values agree with the true value. We can easily distinguish between precision and accuracy by taking the example of dart throwing competition on a dartboard. A dart is a small arrow. This is a dartboard. On the dartboard, the yellow round is the target. Usually it will be smaller. dart hitting within the yellow disc will be accurate. Suppose we have three competitors, Johan, Noel, and Sarah. Each can throw three darts, one after the other, onto the board. We start with Johan, and he is ready for his throw. Now, his first throw, oh, it is out of the target. Now, his second attempt, yeah, that again is out of the target and it is away from the first one. Now, his third attempt, that also is away, and none of his throws hit the target. So, his throws are not precise because they are far apart position and not accurate because it is away from the target. Now it is the turn of Noel. This is Noel. He is ready to throw the dart. Now his first attempt. Oh, again, that also is outside the target. Two more attempts remain. Now his second attempt. Yeah, that also is outside the target. But that second dart is very close to the first one. Now his final attempt. So that also is outside the target. But one thing, all the target hit nearby positions. So his throws are precise but not accurate because none hit the yellow spot. Here comes Sarah. She is ready to throw. Now wait for her first throw. Yes, it hit the yellow target. Now the second one. That also hit the yellow target and also near to the first one. Now her final throw. Oh, that also hit the yellow target and all the throws are very close to each other. Her attempts are precise because all are very near positions and accurate because all the three darts hit the target. Sarah's throws are precise and accurate. So she is the winner. Give her a big clap. Measurements are said to be precise if they yield very similar results when repeated in the same manner. A measurement is considered accurate if it yields a result that is very close to the true or accepted value. Precise values agree with each other. Accurate values agree with the true value. Take the Johans dart. They are far apart, these blue darts, and they are outside the target. So they are neither precise nor accurate. Now come to Noel's dart. They are very close to each other. That is, repeated attempts are very near. So they may be precise, but they are all are outside the target. So his attempts are precise but not accurate. Now Sarah's case, all the three are very close to each other, so it is precise. All the three hit the target, so accurate. Her attempts are accurate and precise. Let us see how we can explain precision and accuracy in an experimental measurement. We have two colored liquids, liquid A and liquid B. Student A is told to transfer 8 ml of liquid A to 3 measuring jars using a burette. Assuming the calibration burette and measuring jars are the same. That means the 10 ml measured using the burette will be exactly equal to 10 ml in the measuring jar. Very often this may not be the case. Similarly, student B is told to transfer 8 ml of liquid B to 3 measuring jars using a burette, assuming the calibration of measuring jars and the burette are the same. And this is the measuring jar. Maximum is 10 ml. And we can measure a minimum of 0.1 ml. So student A took the liquid in the burette, and this is the stopcock of the burette. When it is horizontal, it is closed. To drain the liquid, we have to turn it in the vertical position. So student A start draining the liquid, but he is a bit late to close the stopcock. For colored liquids, very often we take the upper meniscus. This is the upper meniscus. But in this case, the meniscus can be clearly seen. So therefore, we take the lower meniscus. And the value is slightly higher, that is 8.2 mm. The required value is 8 mm. Now his second attempt, he start transferring liquid to the measuring jar. Again, this time also he is a bit late to close the stopcock. So here the value is again 8.2 mm. Now his final attempt. So the third measuring jar. Here the value is 8.3 mm. The required value is 8 mm. But his measurements are very close to each other. The difference is only 0.1 mm. In these two cases, the measurements are the same. So we can say that his measurements are precise, but not accurate because it is away from the required value. It is now the turn of student B. He took the red liquid in the burette, stopcock is closed, and he transferred the liquid to the, so he carefully closed, and the value is only slightly higher, that is 8.1 mm. Now his second attempt, he turned the stopcock on and drained the liquid, and he closed the stopcock carefully, but this time it is slightly less, that is 7.9 mm. Now the final attempt, he stopped the stopcock exactly at 8 mm. So here his values differ by plus or minus 0.1 mm, very close to each other, and this value is same as the required value. So his measurements are both precise and accurate. Questions and answers related to the topics we have studied in this video will be explained in part 2. The link is given in the description part of this video. Thank you for watching. See you in the next video.